2.4 deals with function characteristics. Now to start, I'm going to give you an exercise in using your textbook. So I'm going to ask you to pause the video and use pages 74 to 78 to fill in the 3 charts that I've given you in your notes. If you have not done that already, I'm going to ask you to please pause and do that before continuing. Now that we've all filled in the appropriate information, we're going to go over this together just to make sure that we're all on the same page. So the first thing we're going to talk about is even versus odd functions. So even and odd functions have various special types of symmetry, and those types of symmetry are standard if it's even and or if it's odd. So even functions have symmetry that is considered to be about the y-axis. This means that if I were to take and pick a point on this side of the y-axis and I were to flip it over the y-axis, it's going to have a matching point directly across from it that's going to have a similar value. With even functions, if we're working with it in terms of an equation, if I plug in negative x into my function, once I simplify everything, it should spit back exactly f of x as it was originally given to you. When it does that, we say that it is even. Then other type of function that we have that's common is odd functions. Now, odd functions have slightly different symmetry. Their symmetry is called, it's symmetry over the origin. Okay, so that would be the point 0, 0. So instead of having it flip over the y-axis like it did over here, instead, if I pick a point over here, it's going to have an exact matching point on this side as I flip over this origin. So if I were to draw a little line, those 2 points match up. The equation, or the general form for an odd function, if I plug in that negative x into my original function, it's actually going to spit out negative f of x. So f of x will be the same as long as I can factor out a negative symbol. It is important to note with even and odd functions that sometimes a function is neither even nor odd. So one of the classifications is also neither. The next thing we're going to talk about is increasing and decreasing functions. So increasing functions in general are things that are moving upwards from left to right, where decreasing functions are functions that are moving downwards from left to right. I like to think about this as if I was walking across this graph from left to right, like I would read a book, am I walking up a hill or down a hill? If I'm walking up, it's increasing. If I'm walking down, it is decreasing. Next, we have one-to-one versus many-to-one functions. With these functions, it's easiest to understand or get a definition of both of them before we learn the test to determine which is which. So one-to-one functions are functions where all y values are different, meaning that none of them are going to repeat. So if I look at my graph here, every one of my y values as I continue onwards is going to be different. This is in contrast to a many-to-one function where multiple x values result in the same y value. So an example of this would be a parabola. Now, when we're looking at this, we do have a test to determine whether or not our graph is going to be many-to-one or one-to-one, and it's similar to the vertical line test that we've done for functions, and it's actually called the horizontal line test. So all we do is we draw horizontal lines, and the goal is that we should only cross our graph once, meaning that it is one-to-one. So I've drawn 4 different lines here. All of them cross my graph only once, so this is a one-to-one function. If I move over to my second example, as soon as I draw any line that goes through the graph, I've actually crossed twice. I've crossed here and I've crossed here, meaning that 2 x values have the same y value, and I am therefore have a many-to-one function. So when we get into examples for this, one of the big questions we're going to get is which of the functions is even. In order to do this, we are going to have to plug in negative f of x for each of these functions. So I'm going to start with a. So I'm going to have f at negative x. And I'm just going to use my composition of functions and plug negative x in anywhere that I would have normally seen a x in the original equation. So I'm going to have negative x cubed minus 2 times negative x squared plus 3. Once I'm done that, I'm going to simplify my equation. So negative x cubed is going to give me negative x cubed. Negative x squared is going to give me a positive x, so this is going to be minus 2x squared plus 3. Now, even functions look exactly the same as our original ones we've simplified. So when I look at this, this is not the exact same. It's very close, but we just have this negative floating out front. So this one is not equal to my original f at x. So it is not even. The next example, I'm going to start by doing relatively the same thing. So I'm going to start plugging in negative x for all the x's. So f at negative x is equal to sine at negative x. In order to use our trig functions, we have to have sort of a general idea of our unit circle. So when I look at my unit circle and I think about any point on that, so say this point here, okay, I can go x in a positive direction, or I can go that same distance x in a negative direction. These 2 points are going to have the same value based on our knowledge from Pre-Calc 30 that these points are going to be at cosine x, sine x. Now, sine corresponds to our y-coordinate, so we're going to think about these 2 points in terms of our y values. Here I'm going to have a positive y value, and it's going to be up some distance. Now, when I have that same point but in a negative direction, it's now going to be the same distance, but it's in a negative direction, so it's going to be negative sine. So this is going to be the same as negative sine x. When I look at this and see if it is the same as my original, it is not, so this is not equal to f of x, and it is not an even function. The last one, we're going to start the exact same way that we have every other function. So I'm going to start by plugging in these negative x's. So negative x to the negative 2 minus 2 times negative x squared plus 7. Now, sometimes when we're doing this, it's helpful to remember our exponent laws and knowing that this negative in my exponent means it's going to flip this negative x to the bottom of my fraction. It's going to find the reciprocal. So this is going to be the same as 3 over negative x squared minus 2 times negative x squared is just going to give me a positive x squared plus 7. When I simplify the denominator here, I have negative x squared will just give me 3 over x squared minus 2x squared plus 7. And this is on the bottom. It's not helping me see if it looks exactly the same as this, so I'm going to use my knowledge again of those negative exponents to bring it back up to the top or the numerator. So 3x to the negative 2 minus 2x squared plus 7. Now, this is the exact same every sign as the original f of x. So this is equal to f of x. and therefore this is an even function. The next example asks us to determine the other half of the graph that's not shown. So our domain is -4 to 4, and they've given us from 0 to +4, and they've also told us that it's even. So that means that I'm going to have symmetry over the y-axis. So every point that I have on the right-hand side of the axis is going to be mirrored on the left-hand side of the axis. Think about it as using those red mirror boards that you used in elementary school to replicating drawings. It works the same way. So I'm going to take and just mirror everything as if this was that red mirror board or a mirror, and I'm going to just plot those points. So I should have a point over 2. This point here is going to go through there, and my starting point. And then I'm just going to connect the dots and I have my entire graph from -4 to 4 inclusive. This example asks us to determine whether each function is even, odd, or neither. So anytime we're asked to determine this, we're going to follow what we did in our last example that asked us if it was even, and plug in -x and see what happens. So we're going to start with f at -x is equal to -x to the power of 4 minus 6 times -x cubed. When I simplify this, I'm going to have -x to the power of 4 is just going to give me a positive x to the 4 minus 6, and -x cubed is going to give me a -x cubed. When I combine things here, I'm going to have x to the 4 minus 6 times a -x cubed is going to give me plus 6x cubed. Now, this is not exactly the same as my original, so I know it's not even, but sometimes the check for odd is a little tricky. So my recommendation is always try and factor out a negative to see if that will help us fix any of the signs to make it the same as f of x. So if I take out a negative sign, I'm going to have -x to the 4 minus 6x cubed. Now, this is still not the exact same as my original given function, so I can state that this function is neither even nor odd. Question B, we're going to start by plugging in my -x. -x. Make sure you're using brackets when you do this to make sure that you're not missing any steps or any negatives and making silly errors that are easily prevented. Once I've plugged in my -x's, I'm going to start solving. So I am going to leave this negative here, and -x cubed is going to give me -x cubed. 4 times -x is going to give me minus 4x. When I simplify here, I'm going to get positive x cubed minus 4x. Now, this is not the exact same as my original, so it is not an even function. So I can check for odd. I'm going to pull out that common negative. So I get -x cubed plus 4x. This fits my form of negative f at x. That means that this is going to be an odd function. You can also look at it in terms of when I was in this step here, my numbers were exactly the same, but every sign was the exact opposite as my original. So I did -x cubed, and here it's positive. I had a positive 4x, and here it's negative. As long as every single one is opposite, you can state that it's odd right from this step here. The last question is a little trickier because it has another one of these trig functions in it. So we're going to start setting it up the exact same way as every other by plugging in that negative x. And I'm going to have to do a little bit of reasoning with this one. So I'm going to think back to my unit circle again. And here's some point in a positive direction, x, and some point in that negative x. Now, I know that this point is cosine sine, and we've talked about that in the last example. But cosine and sine do not have to do with tan, which kind of creates a problem. We do know that tan is equal to sine over cosine, though. We learned that in our trig identities. So if one is positive and one is negative, it's going to be negative. And if both of them are positive or both of them are negative, tan is going to be positive. So when I think about this, if I move here, I'm going to have a positive sine value and a positive cosine value, which means that I'm going to have a positive tan value. If I go down in a negative direction to that x point, I'm going to have a negative sine and I'm going to have a positive cosine, because if we think about cast, cosine is always positive in quadrant 4. So right here, I'm going to have a negative sine and a positive cosine, meaning that overall tangent is going to be negative. So this is going to be the same as negative tan x. For the second part here, I have negative 4 times negative x, so that's going to be plus 4x. Now, using one of my two methods, I can look and see, you know what, I have positive tan and negative 4x. Here it's negative tan and positive 4x, so that is the exact opposite. Or I can factor out a negative and say, well, this is tan x minus 4x, and that is the exact carbon copy of my f of x. Whichever way you prefer, this is going to be an odd function. This odd function has domain -4 to 4, and it's asking us to graph the first half of the graph, similar to the other example. Now, with it being odd, that means that we have symmetry about the origin. So essentially what that means is if I go down in this direction to the right, I'm going to do the opposite on the other side of the y-axis, or on the left side of the y-axis. So if I'm going down 1 and right 1, to get its matching point, I'm going to go up 1 and left 1. So I'm going to do the exact opposite. To get the next point here, I went right 1, 2, 3. So I'm going to go left 1, 2, 3. For the last point, I went up 1 and over 4, right 4. So I'm going to go down 1 and left 4. And then I'm going to connect the dots. When I talk about increasing and decreasing, I'm talking about whether I'm walking up that hill or down that hill. I often find it's easiest to do this as I start, like you would read a book, from left to right, and just start by labeling. This is where all my increasing intervals are going to go, and this is where all my decreasing intervals are going to go. So we're going to start at the far left-hand side. So as I start here, if I'm progressing this direction, I'm going downwards, so I am decreasing. I start decreasing at negative infinity, which I cannot include, and I continue decreasing until I hit -2. Now, I'm not going to include -2 because directly at -2 you could argue that I'm also increasing, but in reality I'm actually not doing either. So I'm not going to include -2 in my interval. My next interval from -2 to 0 is going to be increasing because I'm walking up that hill. So I'm going to, under increasing, go from -2 to 0, making sure I don't include those endpoints. The next, I'm going to decrease again from 0 to +2. So this is going to be in union with 0 to +2. And then at 2, I'm going to transition back to increasing all the way to infinity. So from 2 to infinity, I will be increasing.